we are very happy to host Eugene Demler from ETH Zurich, who will speak about optical responses of photoexcited materials from parametric amplification and up to photoinduced superconductivity. So please.
So thank you, Victoria. It's a pleasure to participate in this very interesting conference. I'm enjoying the talks and the discussions. I will tell you about some of the work that we were doing under this kind of general umbrella of pump and probe experiments in solids with particular applications to superconductivity. And I should give credit to people who really did the work. So this is Marius Michael, who was a grad student in my group and recently moved to the Max Planck Institute. Pavel Dolgorov, who is currently a student, and John Curtis is a postdoc in our group. Also what made this work particularly exciting is kind of collaborations which we enjoyed with experimental groups of Andrea Cavalieri and Ray Kaverit. So in a way of introduction, let me start by sort of commenting on things which may not be apparent to people, let's say, who did not follow these developments in terahertz optics. But this has been, like the last decade or so, has been very exciting from the point of view of major experimental breakthroughs. And basically, like what is special about terahertz optics is that this is a frequency range which is particularly interesting for many-body physics. Because if we think about sort of typical electronic excitations, such as quasi-particle gaps and superconductors, charge density waves, or let's say phonons, plasmons, it's all sort of this terahertz range. On the other hand, technically, it has been quite challenging. So it's some kind of at lower frequencies in microwave, we have very powerful sort of experimental tools familiar to everyone, from cell phones, microwave ovens. At higher frequencies, sort of starting from infrared and optical, again, for a long time, we enjoyed quite advanced technology, but terahertz technology has been difficult from the perspective of sort of having powerful sources, having good detectors. But there have been major breakthroughs in the last decades, which really opened the door to kind of a large number of new exciting experiments. And the kind of philosophy of pump and probe experiments can be related to, I guess, our kind of everyday knowledge that if we want to learn about a new person, we shouldn't study them in a sort of very comfortable environment, but rather put them into a stressful situation. And this is exactly what people do in pump and probe experiments. If they want to study kind of interesting state of matter, they first send a pump pulse, usually tuned to some frequency in which absorption is strong, so that there is a like this pump allows strong excitation of the system, and then use a weaker probe pulse to interrogate this sort of this transient state induced by the pump pulse. So the kind of most common perspective for analyzing these experiments until recently has been a picture of quasi-equilibrium. The argument was, well, we can probably, if we think about kind of this generalized landscape of a many-body system, then let's say driving somehow moves maybe a system from a true minimum to some metastable minimum, or maybe even converts a metastable minimum into a kind of absolute minimum of the system. But the expectation and the approach was that, you know, all the probes applied to this transient state of the system can be sort of analyzed from the quasi-equilibrium perspective. So if you want just one simple message from this talk, that is that this is not sufficient. I'll try to take you through a few examples which demonstrate that when we analyze response of photoinduced states, we should really take into account dynamical aspects of the system. We should consider the fact that sort of material, like the way, say, light gets reflected from this material, is strongly affected by the fact that we excited collective modes, and therefore we should use a very different approach to analyze say, kind of light reflection or even light absorption. And I will sort of try to give you like examples, like two examples which come from superconductors, one example which comes from an insulator, and then there are more examples which unfortunately I will not have time to cover. But I think the bottom line is that it's a fairly broad framework which allows to explain a variety of kind of seemingly different experiments. So my talk will be organized as follows. I will first, since I imagine quite a few people did not follow this kind of ultra-fast field, I'll begin by reviewing experiments which motivated us to look into the subject. So I'll pose this as questions. Then I'll give you a simple shortened version of kind of the theoretical approach which we pursue, and then I'll apply this general theoretical perspective to these experiments that we'll discuss in the beginning, and hopefully this together will make a coherent package. Okay, so let's start with experiment number one, and here this is the so-called photoinduced superconductivity in YBCO. Okay, so before I describe like specific experiments, let me give a brief introduction. So consider like a bilayer system, like just a very simple example. So each of the layers we can characterize by the phase of the order parameter, the density of the condensate. And let me just talk about kind of the dynamics of the condensate, not worry about quasi-particles, because we're interested in some low frequency degrees of freedom. So we can write dynamics of the currents, which basically includes simple objects like charge conservation, like tunneling current. So for example, we know that the rate of change of the phase difference is given by the chemical imbalance of the chemical potential, which we can relate to charge imbalance. And the bottom line, and then of course the current we can relate to the phase difference through the Josephson relation. So the bottom line is that we get very simple equation, which looks like a physical pendulum equation, which describes dynamics of the relative phase between the bilayers. And it has a characteristic frequency, which is given by compressibility and the Josephson coupling. So this so this type of excitations are referred to as Josephson plasmons. Now imagine that we make the system slightly more complicated. We have an infinite stack of bilayers, and that's basically a good description of YBCO superconductors. So we have two layers which are close to each other. They have strong Josephson coupling, and therefore they have Josephson plasmon at a relatively high frequency of 15 terahertz. And then coupling between different bilayers is weaker, and therefore we find Josephson plasmons at a small energy scale of 1.5 terahertz. Okay, and so these Josephson plasmons, another way of actually thinking about Josephson plasmons is to say that, oh, it is like a Higgs mechanism, that if we have like superconductors with Meissner effect, then we open a gap in the spectrum. So if we just analyze like the full spectrum of Josephson plasmons, which are analogs of light superconductors, to see that there is a gap at, let's say, at the lowest energies. And this has strong implications for reflectivity. If we take superconducting state at frequencies below the frequency of the lower Josephson plasmon, reflection coefficient is 1. Basically, there are no states like inside the superconductor, so into which external light can penetrate. You can also think about it again as Meissner effect. But then when the frequency sort of crosses the Josephson plasma frequency, we see that reflectivity suddenly drops. So that's what's called Josephson plasma. And then when we go to sort of to higher frequency, there is another drop when we reach the frequency of the upper Josephson plasma, which has to do with this high Josephson coupling. So this is what you get theoretically, and this is essentially what you get experimentally if when our friends measure kind of reflectivity from YBCO in the superconducting state. Okay, and now let's discuss non-equilibrium experiments. So what the group of Andrea Cavalieri found was that if they pump phonons sort of like around frequency of 20 terahertz, something surprising happens. So you can see here, it's kind of color coding of reflectivity for t less than 0. That's basically kind of equilibrium state. The pump pulse has not arrived yet, and it's color coding of like a small frequency. There is reflection, full reflection, and then reflectivity drops. So we see the familiar Josephson Plasmon edge. But when the pump pulse arises, a new edge arises, right, at a higher frequency. So somehow kind of reflectivity changes quite strongly. And but then things become even kind of more dramatic above TC. So, and again, just let me emphasize again, like when we talk about equilibrium properties, the Josephson plasma in equilibrium only seen below TC. Like in this plot, you see a comparison. So 10 Kelvin below TC, there is a Plasmon edge. 100 Kelvin above TC, we just see some smooth reflectivity. So that's why the Josephson Plasmon edge was considered to be kind of the golden standard of observing superconductivity. And now when they pump, here you can see this kind of color coding, or it's maybe more visual. If you look at the change of reflectivity after the pump, you see that there is an edge-like feature, right? So there's like an increase of reflectivity at lower frequencies, decrease at higher frequencies. But something which is surprising is that this Josephson plasma, which we try to convert it into plasma frequency, is even higher than the Josephson plasma frequency below TC. So, and that's why people discuss that, oh, we have there is a light-induced Josephson plasma edge, and since we said that that was a golden standard for superconductivity, therefore it is light-induced superconductivity. But in fact, what's even more remarkable, it appears to be stronger than the equilibrium superconductivity. Okay, so this was the first superconducting example. Let me talk about the second one. Here we talk about a different material, K3C60 buckyball superconductor. So let me first review sort of how equilibrium properties have been explored. So this is kind of, again, optical measurements, but from reflectivity, they extracted real and imaginary part of the conductivity. And you can see that in the real part, so the blue line is below TC, there is a quasi-particle gap which opens up, right? And in the normal state, the red line is just finite. Also notice that in imaginary part, there is 1 over omega tail in the superconducting state, and that is just the kind of usual London equation, that current get accelerated by the electric field. Just from this equation, you can see that this implies that conductivity should be imaginary and go as 1 over omega. Okay, so what that was equilibrium, but now let's look at non-equilibrium. So let's again consider pumping phonons. And something interesting happens again in the real part. We see the gap opening up at temperatures above TC, and we see 1 over omega tail, which appears in the imaginary part, and this shows up even at relatively high temperature. But something which was even more puzzling was that the next step, our colleagues decided to take the same energy of the pump, but compress it into shorter pulses. So when the pump was sort of longish, like around 2000 picosecond, you see that reflectivity was close to 1. Well, that's what we said a superconductor should do, right? At low frequencies, everything should get reflected. But when they made the pulse, the pump pulse, kind of shorter, and therefore more kind of not the same total energy, but at shorter time, therefore it was more intense. So reflectivity became larger than 1. So somehow our material became a gay material, right? Of course, there is no violation of energy conservation because energy is just borrowed from whatever was absorbed during the pump. We're just looking at reflections from a non-equilibrium state, but it's still very surprising how we get this kind of excess reflectivity. Okay, now let's go to the third example. Now we're talking about the insulating material, tantalum nickel selenide. And here again, it's okay. The reflectivity is somewhat complicated. It has sort of reflects various phonons in the system, but let me just focus on the change. So here you can see it's kind of the change, the reflectivity after the pump, like delta R means optical induced change in reflectivity. And we see that the change can be as large, like in excess of 20%. right? But what was surprising is that actually in this case, pumping was done at a relatively high frequency, right? Previously, okay, we were pumping phonons, okay, maybe 20 terahertz. But in this case, pumping was at optical frequency, so it's roughly kind of hundreds of times higher than the frequencies at which we see this change of reflectivity. So, okay, it looks, the question is it kind of related physics or is it something completely different? So what I want to do next is try to offer a unifying explanation for these experiments. So let's actually take a step back and let's sort of look at a problem in optics which even a condensed matter theories can understand. And that is, Fresnel-Flaquier formalism of light reflection. Remember, we have incident wave, just regular plane wave. Then when light goes into the material, the frequency stays the same, but kind of the wave vector changes, right? And in fact, we should find the wave vector through the knowledge of index of refraction, right, by solving this wave equation in the medium. And in order to get analyzed reflection, okay, after we find this wave vector, we just write boundary conditions for electric field, magnetic field, and that gives us the celebrated Fresnel formula. But now, if we want to come up with the simplest version of description of the system in which we excited a collective mode, we can say, well, perhaps what is happening is that index of refraction is no longer constant, but it's periodically modulated in time. And so we can work out details of what exactly a particular mode can do. But now let me just take it as a very generic phenomenological approach. Index of refraction is modulated. So then how do I solve for appropriate electromagnetic modes inside the medium? And we realize that in this case, we should take into account frequency mixing, because when we have time-dependent index of refraction, it can result in a kind of parametric process when pairs of photons get generated. And technically, what this means is that when we when we think about eigenmodes, kind of light matter eigenmodes, they now have a Flaquier character. They mix different frequencies, and these frequencies should be such that they add up to the drive frequency, the frequency at which light is oscillating. And technically, we then have to, if we think that the drive is not too strong, we can do perturbation theory, and we sort of analyze mixing between the modes, which were in equilibrium corresponding to the signal and idler frequencies with the appropriate wave vector, signal and idler wave vectors. Okay, and so it turns out that this problem you can solve, and moreover, quite remarkably, the answer comes out to be quite universal. So if we look at the change of reflectivity in this approach, it has a fairly generic form, which you can see sort of most of the kind of parameters of the change in reflectivity can be expressed in terms of equilibrium properties, and the point where we have parametric resonance frequency, so that we have basically two modes which satisfy energy and momentum conservation and together match the drive frequency. But what is more surprising is that naively you would expect, oh, if I have some kind of parametric resonance, I should always get some kind of like excess generation of photons. I should always get a peak in reflectivity. Or in reality, it's more the situation is more subtle. So we have to look at the competition between damping, and so you can compare it to the kind of phonotype physics. You remember when we have an interference of two channel, and in our case, this is signal and idler are the two channels. They can interfere either constructively or destructively. So and so therefore, in our case, when we look at like what the drive does by mixing idler channel, it does not always result in sort of in the extra peak, but it can also result in a deep, in a shoulder type kind of type of reflection. And the different regimes are determined by the competition between dissipation and drive. Only when we have weak dissipation and strong drive, we get what we would naively expect, an extra peak in reflectivity. Okay, and now what we can do is just use this generic model and look at all these examples. Okay, I'll have to tell you what the collective modes are. So in the case of YBCO, we know that what we start with is we excite apical oxygen phonons, and then these apical oxygen phonons excite Josephson plasmons at finite momentum. Actually, these plasmons at finite momentums can be seen directly using second harmonic generation. So they have been documented experimentally, also by Andrea Cavalieri's group, and you can think about, so with the way how these plasmons are generated, it's again just determined by energy and momentum conservation. We just have to have a lower plasmon and an upper plasmon so that together they have zero momentum, which is momentum of the incident light, and the sum of the frequencies matches the frequency of the phonon. And then two of these lower frequency plasmons at finite momentum, they sort of add up to give us a drive at zero momentum, because when we think about light reflectivity, where it's determined by what's happening at zero momentum. Now what we can do, we can just take the model of the system being driven by the sort of low frequency plasmons, and they're at finite momentum, therefore they can survive even above TC. And we compute a change in reflectivity, and we find a peak, and like both below TC and so in fact below TC it's very sharp, and that's the regime where we have underdamped plasmons, which is what we expect, whereas at above TC we have we have overdamped plasmons, and therefore we have more shoulder-like features. And and the frequency of the drive again is really determined just by the plasma dispersion. So we can sort of predict it just by knowing what the plasma, like what's the energy of the upper plasma, sorry. And because it's relatively flat, then we know what will have to be the frequency of the lower plasma, which is generated. Therefore, we can predict the frequency of the drive. So essentially, this kind of the theoretical model of the excess reflectivity that we get is free. It has very few parameters, just like say like the strength of damping that we have to assume. Okay, so this model then describes the YBCO. Now let's take the buckyball superconductor. In this case, the excitation that appears to sort of give rise to this kind of reflectivity greater than 1 is somewhat more exotic. So if we recall our sort of standard picture of the Mexican cat potential, we know that we have Goldstone modes, which are gapless, and of course in superconductors, this is what becomes Josephson plasmons. But we also have the Higgs mode, right? It's a massive mode where the amplitude of the order parameter changes. And one of the issues about the Higgs mode is that it can decay into lower lying modes, such like as Josephson plasmons. And you can argue, oh, in a 3D superconductor, these are high energy modes, but actually even in like if we take the surface of a 3D superconductor, there are surface plasmons, so even there decay is possible. And the reason, and like one of the kind of manifestations of this decay of Higgs bosons is, let's say, in experiments with cold atoms, when people excited Higgs bosons, what they saw this very broad peak, and this broad peak simply reflected this decay of the Higgs excitation into Goldstone modes. Okay, so how does it help us to explain K3C60? Well, okay, if we take a phenomenological assumption that indeed we suddenly induced a superconducting state and we did it very rapidly, then again, at this model, I will not sort of speculate about what exactly is the mechanism for stabilizing superconductivity. That would be a separate talk, but all we have to know is that kind of if the pump pulse was short, therefore we sort of induce the superconducting state fast. And therefore we quickly go from this sort of potential that has a trivial minimum at 0 to this Mexican hat-like potential. So therefore, if we change potential on time scales short than sort of the equilibrium gap of a superconductor, we will find that our system will not just gently slide into the new equilibrium state, but rather will sort of move in a way so that it will have residual oscillations. And therefore, the time scale for going from this kind of adiabatic to non-adiabatic behavior when the Higgs mode is excited was roughly inverse of twice the gap. And that's exactly where the Max Planck group observed this sort of crossover into amplifying behavior. Okay, but what now that we have an excited Higgs mode, how do we see that it gives us can we see that it gives us non-trivial reflectivity? Now let me show you that indeed, like if we take a superconductor with an excited Higgs mode, we generically expect to find reflectivity that can sort of show amplification. Basically, the way to think about it as follows. So if we have Higgs mode, which can decay into Goldstone mode. So obviously, these are phase twists, like modes which correspond to phase twists in a superconductor, and they therefore they carry current, and therefore they can be converted into photons. So for basically what this means is that the Higgs excitation can generate pairs of photons in such a way that the sum of these photon frequencies adds up to the frequency of the Higgs excitation, and therefore, when the pump pulse, in principle, all of these pairs can be generated, but when the pump pulse arrives with many photons, then we have a Bose enhancement, and therefore the photons which are primarily generated are the ones which have one of the photons matching the frequency of the incoming photons. And therefore, if we have n photons coming with frequency omega-1, we'll get an extra, as a result of this parametric pair generation, we'll get an extra photon with the same frequency and a partner photon with a complementary frequency. And in this case, it's easy to do. It's easy to do kind of even more microscopic analysis of this problem. So what we have to do is just take our usual Maxwell equation, and to find reflection coefficient, we have to relate current to electric field. To remember that in superconductors, current is related to the superfluid velocity, and time derivative of the superfluid velocity is electric field. And in equilibrium, the superfluid density is lambda is a constant. And now all we have to do is just say, oh, as a result of Higgs oscillation, the superfluid density is not static, but it also has a component which oscillates in time. And by adding this, including this oscillatory component of the superfluid density, we can get kind of a good description of experiments in the Max Planck group. And this, as I said, it also explains why this amplification is only observed when the pulses are short, because in this case, we really need to sort of non-adiabatically prepare superconducting state on time, therefore prepare it on timescale shorter than 1/2 delta. Okay, now let's move to the TNS results. So again, as I said earlier, we are trying to understand why we get kind of like this again increase in reflectivity, which is quite dramatic, like more than 20%. But now we begin by exciting the system at a fairly high frequency, at optical frequency, right, rather than the kind of terahertz or even IR frequency. Okay, so if we just take the change in reflectivity and we look at it and ask, okay, let us still assume that we excited some kind of low energy collective mode and try to apply this paradigm of parametric amplification. Can we get a kind of a reasonable description of experiments? And the answer comes out to be yes, we can, but we have to assume that we have parametric driving around 9.5 terahertz. Okay, well, is there anything that's happening at this frequency? Well, in principle, TNS has an IR active phonon, but it has a frequency of 4.7 terahertz. It's not yet clear how it gets excited. So, and then realize, well, actually, clearly, we cannot, like, because of this mismatch of light frequency, we cannot just directly drive this kind of photon by light. However, what can happen is that this pump pulse, it actually changes electron occupations, right? It excites electrons from one of the occupied bands to one of the empty bands. And then the change in the occupation numbers provides an excitation to provide some kind of a push to the phonons. And in fact, there is a strong electron phonon interaction for the phonon at 4.7 terahertz and the electron bands, which are actually being excited by this half electron volt pulse. So, and in fact, one can easily work out so how then the way this coupling works is roughly you can say that, okay, so we have light, we have finite matrix element to go from this occupied valence band to conduction band. And so therefore it's also kind of, it's like an IR type transition. And then it can be linearly coupled to the phonon frequency. But of course, directly this process is inefficient because it's kind of the band gap is much larger than the phonon frequency. So now we can do Schrieffer-Wolff transformation and see, and we will see that in the occupation numbers, the populations of electrons in the two bands, they are now coupled to the phonon display, to the phonon squeezing, right? The square of the phonon amplitude. And therefore, as we said, if as a result of the pump pulse, we change the occupation number of the upper band and the lower band, we will find that we excited not the phonon amplitude directly, but rather the phonon squeezing. And because it is phonon squeezing, so you can really think about it as just Q squared changing, whereas the average value of Q stays around 0. And therefore, by exciting Q, and this explains why you actually see that what gets excited has a frequency of twice the phonon frequency. So it's 9.5 terahertz, even though the phonon that sort of is important is at 4.7 terahertz. Anyway, so with this, we can actually get kind of a reasonable model, just like so. And Pumpprobe and his group provided first principle calculations to show that indeed we can identify like specific transition of electrons, and they checked indeed the nature of the coupling of those electrons to this 7 terahertz phonon. So there is one curious fact. Okay, so that you know that there are some debates whether this material is discussed in the context of excitonic transition, and there are debates: or is it really being driven by electron-electron interactions or by electron-phonon coupling? So what one finds experimentally is that this kind of pump-induced change in reflectivity only shows up in the low temperature phase. And indeed, like by doing first principle calculations, again, the group of Angel Rubio confirmed that this strong electron-phonon coupling only appears in the low temperature phase, but not in the high temperature phase, and which explains. So at first we thought that there must be some symmetry reason, but again, so far we did not. It's like in the high temperature phase, it's not identically 0. It's just much smaller. So again, so if there is some symmetry argument for why this sort of for this enhancement of electron-phonon coupling in the low temperature phase, we don't know it yet. Anyway, so my time is up, so I'll just conclude, and I try to argue that we now have another kind of paradigm for interpreting pump and probe experiments, that we should not only think about properties of transient states as just evolution in some kind of energy landscape or stabilization of some metastable state, but rather we should seriously take dynamical nature of these transient states and analyze light reflection from such kind of systems with excited collective modes. And fortunately, it appears that that there is a pretty generic kind of pattern in how this pump-induced changes in reflectivity can look. So therefore, even if we do not, let's say, have access to like super detailed microscopic model, we can sort of check this kind of this Flaquier model of pump-induced changes in reflectivity, like up to a couple of constants. And already this type of approach explains, let's say, different few examples between among insulators and superconductors. Thank you.
Okay, thank you very much. Very intense. Very intense. Okay. Oh, wow. We have a lot of questions. I also have questions. Let's start from Tero.
Thanks for the interesting talk. I have a question about the role of disorder. So you assumed in various places momentum conservation and so on, but
you should be careful. No, I did not. No, I did not. You see, when things are happening on the surface, I did not really assume momentum conservation. Like basically, what happens parametric resonance, like where it is enhanced, like is for bulk modes which satisfy no momentum conservation. But okay, but maybe I'll let you finish your question.
Yeah, especially, I mean, we studied sort of, and especially my colleague Mihal Silaev studied Higgs mode sort of excitation recently, and he showed that actually disorder makes the coupling to the to the external fields much stronger. So this might be
again, like you see, like when we talk about the terahertz, right? We talk about really long wavelength in vacuum, right? I don't know, like fraction of tens of a millimeter, right? And I emphasize that. So like when we talk about the dispersion, let's say, of plasmons, right? As long all I need is that on this sort of very long wavelengths, I have a well-defined collective mode. But when I solve light reflection problem, I solve it exactly, right? So I do not obviously like in the direction perpendicular to the surface, there is no light conservation. So like therefore, like I did not, maybe it wasn't clear when I said, oh, like okay, what the condition of the parametric resonance, it's more or less the condition from the point of view of collective modes, but we really talk about very long wavelength excitation. On this long wavelength excitations, like like Josephson plasmons, they will not be affected so strongly by momentum non-conservation, right? We really talk about, as I said, very long wavelength modes, very low frequency.
Okay.
Okay, thank you. I will quickly ask very quickly. So do I understand correctly, you were speaking about the decay of Higgs bosons or Higgs modes into Goldstone modes. Is it correct?
I gave it as an illustration. Like technically, the only thing I needed, right, was the fact that if we modulate superfluid density, like the superfluid amplitude of the order parameter and changes superfluid density, I did not describe it in the language of decay of Goldstone mode. That was just to sort of get some intuition.
Because normally, I mean, Goldstone mode is eaten up by Anderson Higgs mechanism, so that it becomes gap.
But as I said, not on the surface. Remember that on the surface of a superconductor, we can still have gapless mode. Like in 2D, as you know, there is no finite gap, right? There is a square root dispersion, and the surface is like a 2D superconductor.
Okay, thank you. Then Jonathan.
Hi, thanks. I guess my question is related, so feel free to just pass over it. But you mentioned this condition for basically impulsive stimulation of the Higgs mode was that you pass non-adiabatically from the normal state to the superconducting state, so that you basically have oscillations instead of just transferring it to the minimum of the potential, which makes sense to me. But then it also seems like there's another constraint, which is that you then have to turn on you basically have to switch the Mexican hat potential for long enough as compared to like the escape time from the unstable equilibrium, so that it doesn't, because there's nothing to like, otherwise it has to tunnel or something out, and that seems like it could be a bottleneck also.
So John, I guess I'm not sure I understand. So there are several, I think I can see several layers of questions in what you asked. first you are saying, oh, I gave a very simple picture of sort of monochromatic drive. You're saying, oh, if there is a finite decay time, then it's a drive like so that's multi-tonal drive at several frequencies. So is this important? So quantitatively, yes, and but like what I showed you, it was already in the perturbative regime. So in that case, it was actually what we could do. We could just decompose, kind of drive into several Fourier components and add them all up, and the answer would not. I mean, it would not change much unless the decay is ultra short. Like if you do not have a single oscillation, then of course, yeah, like it would not work. So is this what you were asking, or?
Okay, I think maybe it was in a different. Maybe now I'm thinking it was just a toy example. It was basically transition from normal state to superconducting state, but I guess that's not actually what you considered in this example.
Yeah, I'm right. So I'm not like, first of all, okay, I do not need kind of true long range order to be established, right? For me, it's enough to have, to have some kind of short range correlations, right? I really just need, because what matters to me is redynamics at finite frequency scales, right? And as I said, I'm trying to be agnostic at this point. I'm just sort of taking as a model that somehow, yes, indeed, we assume that the pumpholes stabilize superconductivity, but I do not want to. I have, of course, my favorite theory, actually, at least a couple of favorite theories for why this is possible, but they are irrelevant for this discussion.
Yeah, it's fine. Thanks.
Okay, and now Fabio. Fabio, did you unmute? I don't know, maybe he raised hand and then forgot. Okay, we have Jose. What happened? Yeah, okay.
Yes, thank you for a very interesting talk. I was curious about the last things you were mentioning. You say, I mean, usually we see this appearance of the plasmon as essentially this induced superconductivity in Cavalieri experiments.
Sorry,
right?
can you speak up? I cannot hear anything.
Okay, can you hear now?
No, I can hear better, yes.
It's even worse?
No, it's better.
Okay,
Yeah,
okay.
Just maybe just closer to the microphone.
Okay, no, just that. Okay, let me raise the level. Okay, yeah, you often. I mean, we often see these experiments in which a plasmon appear after some terahertz drive as the essence of this light-induced superconductivity in Cavalieri experiments. But now in this C60 experiments, you say there is another mechanism for light-induced superconductivity. Am I right? I mean, I'm a bit confused of what.
No, okay, for the plasmon story, what's for YBCO?
Okay, but with this is not universal, you would say. I mean, it's not. I mean, that's what we usually understand by light-induced superconductivity, and we thought it was a unique mechanism. But
Yes.
you're thinking now there are several. I mean, in different materials.
No,
I mean,
no. Okay, so sorry, I could not hear what you said at the end.
I'm wondering if we should think of different situations in different materials. I mean, and that's not a kind of universal mechanism for light-induced superconductivity, this parametric amplification.
Okay, I'm saying that when we think about optical reflection properties of superconductors after the pulse, we should not analyze them from the perspective of equilibrium superconductivity, because like YBCO is even more striking. If you try to extract the new Josephson plasmon H, it is larger than the kind of Josephson plasmon H below TC. So it's as if you induced Josephson coupling stronger than in equilibrium.
Yeah.
Sort of, it sounds so surprising that it doesn't make sense. On the other hand, if I take dynamical perspective, if I say that, look, what has happened in YBCO is that the drive excited finite momentum excitations. Let me again show you the picture. Sorry, just get.
I just want to add, while there are really many different mechanisms for light-induced, light-enhanced. There are this Flaquet squeezed phonons with electrons, something else. There are lots of ways, not necessarily Josephson plasmon.
Oh, thank you, Victor. Actually, you know this.
I want to know his
Squeezed phonons and enhancing electron phonon coupling. That, of course, is one of my favorite mechanisms since we worked on this. But no, but I think it's sorry. Can you see this?
Yep.
Yes.
So, but you see, again, the frequency. My point is, you excited a phonon. This phonon generates these excitations of plasmons, and we can actually tell what is this frequency of the lower plasmon because it's a phonon frequency minus the energy of the upper plasmon. And then the peak in reflectivity, both above and below TC, is basically that frequency, right? Which is higher than the Josephson plasmon H, which would be at Q equal to 0. So now the fact that the photo-induced Josephson plasmon H is at higher frequency, both below and above TC, is kind of reasonable. It makes sense. That's how it should be.
Okay, but
you
don't think that that similar mechanism applies to C60? The C60 mechanism is something
again in K360. So what is the lesson here? Like saying YBCO, I'm not saying it's so the lesson that we can extract from here is that above TC we do not have long range order, but we have enough of short range correlations to have plasmons at finite frequency and finite momentum.
Okay.
Therefore, my answer is it's not photoinduced superconductivity. It's rather a way to reveal plasmons at finite momentum and finite lifetime, but because they're at finite frequency, that's sufficient, right? So therefore, like in YBCO, it's not an experiment which says, oh, we use pump to induce superconductivity, but rather we used pump to reveal short range correlations.
Okay, that's what okay, thank you very much. That's what I was thinking. Okay.
So in K360, on the other hand, my goal was to show that, I do believe that there is a mechanism of photoinducing superconductivity or metastable superconducting state. But my focus was, well, even if you induce superconducting state, how do you get reflectivity greater than 1?
Okay.
See, like in a perfect superconductor, you can only get reflectivity equal to 1. But in that case, what was observed that if the pulse was short, reflectivity was getting larger than 1. As I said, I am like for this part of the discussion, I don't care how superconductivity was induced, but as long as it was induced dynamically and we excited a Higgs mode, then we can explain why this superconductor becomes a gain medium for terahertz radiation.
Okay.
I think
everybody thinks that the IPCO story, I mean, a lot of people think that the IPCO story is